Welcome back, everybody. We are in week 7, and that is our the video session for going over the guided activity for this week, Lab 7, and this is our second video. So we just calculated the confidence interval at the 90% level, and we'll continue on with the activity. So we decided that we can, with 90% confidence, say that the average IQ of mothers of kids that are gifted, that have the gifted trait, is somewhere between 116 and 120. Now let's make a decision about the hypothesis and interpret in the context of the research question. Let's recall our hypothesis. The null hypothesis is that the average IQ of mothers of gifted children is 100, just like the typical population, and the alternative hypothesis is that the average IQ of mothers of gifted children in the population is greater than 100. What we have here is that 100 is not part of this interval. It's not contained in this interval, and the interval is actually all above 100. So 116 is greater than the typical value for the population. So the confidence interval tells us that any value within it could conceivably be the true population mean. In particular, we are 90% confident that it includes the true population mean. The null value of 100, as I said, is not included in the interval. So it is not a plausible or likely average IQ score of mothers of gifted children. And it is actually smaller than the lower boundary of the interval, right? So 100 is less than this lower boundary. Therefore, we reject the null hypothesis that the IQ of mothers of gifted children is just like the IQ in the general population. So the interpretation here is that there is convincing evidence that mothers of gifted children have higher IQ than adults in the general population. So again, this statistical inference, because we're using data of one sample to make an inference about what happens in the full greater population of mothers of kids that are gifted, right? Therefore, the gifted trait in children is related to the intelligence of their mothers, it seems. Now, let's look at another way of using sampling distributions and the central limit theorem to test hypothesis using the z-tests. Now, what we've just done using the confidence interval is a quick and dirty approach for hypothesis testing. However, what it does not do is tell us the specific likelihood of certain outcomes under the null hypothesis. In other words, it does not tell us the p-value based on which we can make decisions on hypothesis. Now, a few classes ago, we learned how to get the p-value by running or simulating a random experiment. Do you guys remember? We used that to determine the likelihood that a 30% difference in promotion decisions of a male versus female candidate would happen by chance alone. What we used is a simulation-based method that I told you at the time that it's not the most typical way that statisticians actually go about testing hypotheses. So today we'll learn a more traditional method, a method to determine p-values, the likelihood of a particular pattern in the data under the null hypothesis that are based on the central limit theorem. That is, we'll use the CLT, the central limit theorem, not a simulation or random experiment, to estimate the sampling distribution of the mean under the null hypothesis. The meaning of the distribution is exactly the same. So once you know how to generate that sampling distribution, you should basically be halfway done with testing the hypothesis. The p-value, one more time with feeling. The p-value is the probability of the observed or more extreme outcome under the null hypothesis. Going back to our example of gender bias, the p-value in that context refers to the probability of finding a difference of 30% or greater under conditions of pure chance. that is, under the null hypothesis. The null hypothesis was that the expected difference in the population would be equal to 0 in that case, if no gender bias was at play in promotion decisions. Think about this question for a second. In the experiment we just discussed, investigating the IQ of mothers of gifted children, what would be the probability we need to compute? The probability we need to compute here, let me put the answer, is the probability of the observed average IQ or higher if the sample was simply drawn from the population at large. That is, if the null hypothesis was true. In this case, if the average was 100, assuming that the population of mothers with IQ, the population of mothers of gifted children had an IQ of 100, right? Assuming that, what's the probability of observing the particular average IQ that we observe in the sample, right? Okay, so let's go through that process step by step. Research question driving the analysis. Do mothers of gifted children have higher levels of IQ than the overall population? Step 1, set the hypothesis. Null hypothesis is that the mean, the average of the IQ of mothers of gifted children is 100, just like the typical population. The alternative is that it's greater than 100. Now let's start building a table with the important information that we will need in the end. We'll build it step by step, and then I'll show you how to do this in a more efficient way. Let's start building a table with the important information then. One important piece we already have is the sample size that we know is 36 and the expected mean of the population of mothers of gifted children under the null hypothesis, and that expected mean is 100. We will continue to build this summary table as we go through the steps. So I'm using the function summarize. I am putting here the data set that we're analyzing. I'm asking R to compute the number of observations in that data set. And I'm simply telling R that the average related to the null hypothesis is 100. If we run this, that's the output that you should get. Now, step 2, we need to compute the point estimate of the population parameter of interest, the observed mean IQ of mothers of gifted children. So that is just the mean of the variable IQ, and we're going to call that X bar because that's the symbol for the mean of a variable in a sample. Remember, mu is the symbol we use to refer to the mean of the population, the thing we want to estimate, and then X bar is the symbol we use to refer to the mean of the sample. So if we run this, now we have our table with the number of observations, the mean, the average IQ under the null hypothesis, which is 100, and the actual average IQ that's observed in our sample, which is 118. All right? So the observed IQ in our sample, that is our best point estimate of the IQ of mothers of gifted children in the population, is 118. That's greater than what would be expected if there was no difference between the IQ of mothers of gifted children and the IQ of the population at large, which is 100. Question 3 for you to think about. Why can't we simply use this to make an inference about the identified hypothesis? Why can't we just see, look, 118 is greater than 100, so let's just assume that mothers of gifted children do have a higher IQ. Why can't we make that conclusion just by looking at the estimated mean? If you thought it's because of sampling error, you are right. Because if I get a bunch of samples of mothers of gifted children from the population at large, even if the true average in the population is 100, every time I sample, I won't necessarily get exactly 100. It will have some variation, right? So that's why I need more than just looking at these differences. I need a statistical procedure to tell me what the probability is of getting this average of 118 if the true average in the population is 100. So I'll read again to make it more formal. Why can't we just look at the average, see that it's greater than 100, and simply decide that, yes, the alternative hypothesis is true? The answer is because of sampling error. If we sample from the population of mothers of gifted children multiple times, the sample means will vary. So even if the true average IQ in the population is 100, it will not necessarily be 100 in any given sample. Before we can conclude anything different, right? Before we can say, for instance, that the IQ is actually greater than 100 for these mothers, we need to know whether a sample mean of 118 is a plausible, a typical outcome if the sample comes from a population whose average IQ is actually 100. That's why we need inferential statistics. So to be more precise, we want a p-value, a probability value, that will give us the probability of observing a mean IQ of 118 or higher if the average IQ of the population of mothers of gifted children is actually 100. So what do we need to get the p-value? Well, we need the expected distribution of x bar, the expected distributions of mean IQ, the sampling distribution of the mean, under the assumption that the IQ of mothers of gifted children is no different than the IQ of adults in the population at large, or simply under the assumption that the null hypothesis is true. Now, we can't simulate the distribution the same way that we did for the gender bias study. But if particular conditions are met, we can use the central limit theorem to construct that sampling distribution of x bar under the null hypothesis. This takes us to step 3. So step 3 is to check the conditions to estimate the sampling distribution of x bar using the central limit theorem. These are the same conditions for computing the confidence interval we just did above. We checked that, so I'll just copy the answers here. Do we have independence of observations? Yeah, we can assume independence because the sample is random, and 36, the sample size, is less than 10% of all gifted children, of all mothers of gifted children. With respect to sample size and skew, we have a large enough sample of greater than 30, and really the distribution is not that skewed, it's really nearly normal. So we can use the central limit theorem to construct our sampling distribution. And the central limit theorem tells us about what the shape of the distribution is, the mean, and the spread. So given that the central limit theorem holds, we know that x bar of IQ, the distribution of means of IQ if I were to repeatedly sample from the population, is nearly normal. The mean will be 100 because we want a sampling distribution of the mean, assuming that the null hypothesis is true, assuming that the mean IQ of the mothers of gifted children is 100. So we'll have 100 in the middle. And then the standard error will be estimated from the standard deviation of the sample. That's the standard deviation divided by the square root of sample size. So let's continue to build our table. So we have the number of observations. We have the mean, which is the center of our sampling distribution under the null hypothesis, which is 100. We have the observed mean IQ in our sample, and we can also compute the standard error. I'm adding that to the table here, which is the standard deviation of our IQ variable divided by the square root of n, which I computed just here. Now, it is very useful to draw the sampling distribution and shade the area corresponding to the p-value we wish to estimate. So try to sketch it out, and we'll start the next video with that sketch in order to compute, and following that, we'll compute the z-statistic and the p-value associated with it. I'll see you in a bit.